Hello, my name is Evgeniy Shapiro. I'm the Fluids Product Manager at Ricardo Software. In this workshop, I will introduce methodology for fast calibration of WaveRT engine digital twins using surrogate optimization and demonstrate its implementation in Ricardo Software Suite. The methods and tools we'll be discussing in this workshop are available in Ricardo Software 2022.1 and later releases. We will start the workshop with a brief introduction to WaveRT engine plant modeling and its key features, followed by the description of model calibration process and potential approaches to model calibration, where we will talk a bit more about why, in our view, surrogate optimization is the best candidate for model calibration tasks and what the typical calibration parameters are. Then we will illustrate how this approach can be used in Ricardo Software Suite using our R-Desk Tuner tool on a workstation or high-performance computing cluster for an example model. Finally, we will talk about examples of more complex calibration tasks and accuracy and scalability of our R-Desk Tuner. At the end of the workshop, we will answer your questions about this new technology. If you are watching an offline version of the workshop, please email your questions to rs_support@ricardo.com. Let us start by introducing WaveRT as a digital engine twin creation tool. Engine twins are essential for virtual product development, as well as diagnostics and control of existing hardware. Not only they allow us to develop better powertrains, but also to do this much more cost efficiently. So what are the essential properties a digital twin should possess? Firstly, accurate physics is essential. We know that the combustion processes in an internal combustion engine are extremely complex. Yet, we need to be able to capture them predictively in order for the digital twin to be applicable across a broad range of conditions without the need for recalibration. Secondly, fast simulations. In order to have a real digital twin capability, we need to be running at least at real-time speed. But in practice, it's usually useful to run much faster than real-time. When using the twin in software, a faster plant model allows us to accelerate development and calibration, particularly when we need to exercise the model over the durations of a drive cycle. On hill platforms, where the hardware can be more constrained, running engine model much faster than real time frees up part of the hardware resource for other tasks. Finally, the output of the digital twin model has to be compatible with standard hardware and software platforms for use in hardware-in-the-loop, software-in-the-loop, or model-in-the-loop contexts. In this workshop, we will demonstrate how Ricardo WaveRT satisfies these requirements. So, what features of WaveRT enable it to be the best digital twin solution available on the market? Firstly, it uses fully physical plant modeling approach. It brings a level of realism which is only possible for true predictive simulations, including predictive combustion modeling. It is compatible with industry standards for model-in-the-loop, software-in-the-loop, and hardware-in-the-loop, and supports all the widespread hill platforms. Importantly, frequently when we are talking about engine digital twin, there is a process of reduction of fidelity when going from the 1D model running on a desktop to a 1D model running in real time. WaveRT doesn't simplify the model. All elements are translated one-to-one without loss of fidelity. Finally, it delivers modeling process which is based on decades of Ricardo's expertise in engine design and calibration. So how fast is fast when we're talking about faster than real-time digital twin? An example here shows a typical 1.5-liter 3-cylinder direct injection modern gasoline engine. In this model, both donor Wave and WaveRT have 134 model elements. Wave features variable time step. WaveRT typically runs at a fixed time step, in this example 27 microseconds, corresponding to 1 degree crank angle resolution at 6000 RPM. Under these conditions, WaveRT is 2.5 times faster than real time. When running on a conventional laptop hardware, Intel i7 CPU clocked at 2.6 GHz. Let's have a look at the WaveRT modeling workflow tasks, taking us from hardware to a digital twin model. The starting point for us can be the leading engine application in hardware. This leading application is then mapped to a 1D model, either in Wave or in other tools such as GTPower, from which we can import a model to Wave with a single click. The Wave model is going to be used as a donor model only, although users may choose to calibrate and run the donor model as well if it is required for applications other than digital twin creation. The Wave model is directly translated to WaveRT through a one-click export. The number of elements is the same in the donor model and WaveRT model, and there is no complexity reduction. The RT model is then calibrated using our R-Tuner tool versus the target dataset or versus donor dataset if you want to replicate the behavior of the donor model. Calibrated RT model can then be used as a digital engine twin in vehicle-level applications in software or hardware as a standalone shared library or an FMU. WaveRT supports all widespread hill systems, and in general, we support everything with a conforming C compiler. The whole process takes from 1 to 3 weeks, depending on the complexity of the model, experience of the user, availability and quality of the test data and computing resource. However, the time required for conversion and tuning of a valid donor model into a real-time twin is typically under 1 day. So why do we need to calibrate models? Fast-running 1D CFD engine models feature a number of uncertainties. These uncertainties are introduced, for example, by lack of 3D representation for essential 3D phenomena, such as turbulent mixing, semi-empiric modeling present in 1D, approximated heat transfer. These uncertainties are typically addressed through calibration or tuning parameters. The tuning process aims to find a set of tuning parameters that maximize the quality of fit between the model and the reference data. Ricardo R-Desk Tuner automates this process, minimizing the amount of manual work required and engineer time spent. The example on the left shows the initial and final state of the tuning process with error bars on the measurement data. The objective is to get the model to fit the data within the required accuracy, bearing in mind the uncertainty of the reference data. The actual tuning process is fairly generic and doesn't really depend on the algorithm involved. So the process varies selected model parameters in order to improve the cost function until stopping criteria are met. Cost function measures agreement between simulated and the reference data. The tuning starts from initial conditions that are based on initial values and bounds of tuned parameters. The process then aims to find the best model within these bounds. Based on this, the algorithm proposes a model. The model is basically a set of values of tuned parameters. Then this model is evaluated for selected operating points. Evaluation in this context means running WaveRT simulation at each operating point with the selected set of parameters. Selected outputs from these simulations are compared to reference data, and then the match is measured by the cost function. WaveRT and R-Desk Tuner use chi-square cost function based on inverse problem theory. Tuning algorithms or minimization algorithms are typically classified into global and local. Global algorithms have higher probability of finding the only global minimum of the cost function, but at the expense of higher computational demands. R-Desk Tuner supports both types of algorithms, starting with global surrogate optimization, which constructs and progressively updates an approximation of chi-square function to save computation time. This method is global, multidimensional, doesn't require calculation of derivatives, and samples the problem space stochastically. In the image, you can see minimized test ACLI function and the surrogate function after 10 evaluations of the ACLI function. R-Desk Tuner implementation is based on Cornell University work on PySort and POAP Python libraries. R-Desk Tuner also supports two local methods. Downhill simplex, a local multidimensional derivative-free method, which is a direct search. It creates a polytope or a simplex and does a predefined set of operations to search the parametric space. In 2D, the simplex is a triangle, as shown in the image. R-Desk Tuner also supports Brent's method, which is a descent method combining golden section with acceleration via inverse parabola fit. A typical tuning process can be constructed as a chain of consequent optimizations or tunings with different algorithms. However, for the majority of engine model calibration tasks, it is sufficient to use only the first option, surrogate optimization, as we will illustrate. So what are the benefits of the surrogate optimization? Firstly, it's simple. It requires low a priori information. It only requires specification of the search space with bounds, and you can start the tuning. Secondly, it's accurate. The algorithm is unlikely to fail in the first minimum it finds. Instead, it includes excitation mechanism that makes it keep exploring the parametric space. Hence, high probability of finding optimal solution. It can be used to simultaneously tune all engine calibration parameters, which also accounts for possible correlations between these. But above all, it's highly parallelizable and evaluations are fully independent. Global methods are computationally expensive, typically requiring large numbers of evaluations. And let's recall, every evaluation includes running an engine digital twin for sufficient time for it to reach a statistically stationary state at a given operating point. Here, the benefits of WaveRT come into play. Firstly, it's running much faster than real time, which speeds up individual evaluations. Secondly, it includes advanced features, such as being able to restart an engine model from a pre-warned state, which reduces the time required for the model to converge. And finally, R-Desk Tuner is highly parallelizable and takes full advantage of multi-core workstation and high-performance computing cluster hardware. As a result, an engineer can take full advantage of the benefits of the algorithm and compensate for the computational expense by simply increasing the number of cores available for the simulation. So what tuning parameters can be used to calibrate the plant model? The choice of tuning parameters may depend on the engine type, for example, whether it's a naturally aspirated or a turbocharged engine. When working with VB-type prescribed combustion models, the tuning parameters typically include these of heat transfer and catalyst friction to control the pressure drop. For predictive combustion models, turbulence modeling parameters and combustion modeling parameters become important and should be added. These parameters are calibrated to achieve best accuracy with respect to total airflow, IMAP or torque, with additional controlled quantities introduced for more complex cases to control pressure in the system, for example, compressor inlet catalyst outlet pressure, intercooler exit pressure, etc., and temperatures in the system, such as, for example, turbine inlet temperature. Finally, when tuning to results of 1D donor model, or when considering an instrumented engine, piston liner and head temperatures can be included. Let's have a look at an example model of a tuning process for a simple model of a turbocharged diesel engine. In this case, we will work only with heat transfer coefficients for open and closed part of the cycle and attempt to match engine airflow and torque. The selection of the example is based on its simplicity. We have 24 operating points here and 2 tuned parameters, 2 engine outputs, which means that we'll be able to illustrate the tuning process in real time. Let's get started. First, let's have a look at our example. In our simplified 1.6 liter diesel engine, we have added instrumentation which allows us to control the model externally when it is exported into a real-time environment. So firstly, we have an airflow sensor, and this sensor will be used to determine the airflow in the model. It's also used to determine the fueling, as you can see here, so we send airflow to the fuel controller. It also has a torque sensor, which is the second of our target functions. The tuned parameters are HTVC and HTVO, so heat transfer multiplier at intake valves closed and heat transfer multiplier at intake valves opened, which are attached to cylinders 1 to 4. Now, our test model contains 24 cases with speed ranging from 1000 to 6000 RPM, and it also contains target airflow and torque data, which we should be using to build our cost function in the tuner. So let's start by creating a real-time model from this donor. I'll start by adding WaveRT expert solution and set the mode to export and compile and generate sensors and actuators and parameters for this model. We can run this expert as is, there's nothing else which is required. However, our tuner will run faster if we enable convergence. So let me switch on the cyclic convergence detection, set it to 25 cycles, and add convergence criteria. Since our targets are airflow and torque, let me add convergence criteria for airflow and convergence criteria for torque. Keeping the tolerance at default relative 10 to minus 3. Let's save the model and run the expert. We could also enable a restart file and pre-warm the engine, which will further speed up the tuning process. But as we will see for this particular example, it's not necessary. The tuning is fast enough even without restart functionality. That's it. Our model is ready. Now we're ready to start our model calibration. I will add a WaveRT tuning task and load the library we have just created. At the moment, I'm working on a Windows laptop, and if I use the same machine for tuning, then I can directly tune the shared object which was just created for my real-time model. It is more frequent, though, that when we're working with HPC clusters, the HPC cluster runs Linux operating system. So in this workshop, we'll demonstrate submission from a Windows laptop onto a Linux cluster. In order to enable that, I'll instruct the tuner to compile WaveRT model at the destination and link it to the expert task, which we have just created. Expert task will provide the compilation options and all the information required for the tuner to compile the model. All of the other parameters can stay at defaults. Now let us define the tuning process. First thing I'll do is I'll set the operating conditions. Operating conditions correspond to the values which are defining operating points in my case table. These are, in my case, speed, target equivalence ratio, and ignition start of combustion. We need to map them to the inputs of the real-time model. Speed actuator, target equivalence ratio actuator, and start of combustion actuator. The tuning will be using case set, which corresponds to our 24 operating points, and I will increase the batch size a bit. Batch size determines how frequently the surrogate function is reevaluated, and for simple cases like this, it's sufficient to evaluate it in batches of 4, which will also speed up the execution time. Next, we need to define the tuned parameters. What are we going to tune? In our example, we're tuning HTVC and we're tuning HTVO, so 2 multipliers for heat transfer in the cylinder when valves are closed, heat transfer when valves are open. I'll set the initial value to a wave default of 1 and give a fairly broad lower and upper bound to challenge my surrogate optimization to find the right solution. And I'll also give them some names, HTVC and HTVO. Finally, we need to specify what are we aiming to achieve in the calibrated model? This is done by specifying fitted parameters. For fitted parameters, we define airflow and torque. These are our two targets. A WaveRT sensor corresponding to target airflow is S underscore airflow. WaveRT sensor corresponding to target torque is S underscore torque. The most important question is how we are specifying the error and error type. So we typically recommend using relative errors unless the requirements of the project specifically set bounds on absolute error required. And for airflow, we'll set 2%. For torque, we'll set 2%. When the error of measurement is available, then these errors correspond to the error of measurement. When the error of measurement is not available, then we can use guidelines provided with WaveRT, which are 2.5%. And what these errors do is the tuning cost function grows rapidly if we are out of bounds by more than the specified error percentage. So the tuning is fully defined, and now we can define where we will run the tuning. This is done by specifying the host. If I run the tuning locally, then I'm using the local setting, but my laptop is probably not the best place for large-scale surrogate optimization, so I'll be using our Linux test cluster. For this cluster, I need to specify the number of cores available. I'll set it to 71. There are 72 cores available for me, but one of them is reserved for the master process, which manages the surrogate optimization. And because I'm submitting from Windows laptop to a Linux cluster, I'm working on a shared drive, which is visible to both my laptop and the cluster. And I need to map the directory where I'm working from my laptop to the cluster where the execution takes place. So I'll call it, for example, cluster RQS. And I'll specify the path on the cluster, which in my case will be mapped underwork Galileo cluster RQS. Also, since I'm submitting from Windows machine to a Linux machine, unless my environment on the Linux machine already contains path to the correct installation, I need to specify where to find the executables for tuning. So because I don't want to modify my Linux user environment, I'll specify the path directly here, path to our 2022.2 installation. The host file stays the same. The submission script stays the same. The queuing system. For the queuing system, I'll be using Ricardo queuing system, which we are providing in the installation, which features a number of benefits, but one of them, and an important benefit, is that it allows submission from Windows clients to Linux HPC resource. To utilize my cluster, I'll tell my queuing system what is the head node. In our case, it's RSO1. And what is the name of the job? For example, test diesel tuning. Finally, the tuner is based on MPI, and I can prescribe MPI parameters. These are specific to the configuration of the computing cluster. In my case, I need to tell MPI to propagate the path environment. And I need to tell MPI the best way to use InfiniBand. The last collapsible shows the submission command, which also can be run from the command line to enable HPC submission. Now everything is set up and I'm ready to start my tuning. So I'll go to my WaveRT tuning solution and launch it by pressing on the Running Man icon. At this point, the model is translated and R-Desk performs a number of checks that the setup of the tuning is correct and all the points of communication between the tuner and the real-time model, that is sensors and actuators, are set up correctly. And if everything is okay, the model is sent to my HPC cluster, which I can see here in the output window, and it appears in my queue, which tells me that I have this job, which runs on 72 cores. The process is decoupled. The job is now managed by my HPC cluster, so there is no direct feedback to R-Desk. However, I can follow the progress of the job either by looking at the job results and monitoring them in real time, or by looking at the log files which appear in the directory where the tuning is running. And the log file shows me the progress of evaluation, normalized cost function, and the current values of my tuned parameters, HTVC and HTVO multipliers. The default setting of the surrogate optimization in R-Desk Tuner is to run 50 evaluations per tuned parameter. I have a fairly simple model, so I have only 2 parameters. So we can expect 100 evaluations to take place. The model is about complete. The tuning is about complete. The results are finalized and the tuning has finished. It took 2 minutes to obtain the solution. The tuning has completed and we can examine the results, but before examining the results, let's add an additional data set. I'll clone the tuning, deactivate the original one, and change the type of the second tuning to validation. The validation tuning is designed to provide a set of results for all the operating points, but for a fixed value of tuned inputs. So in my case, it will give me a data set at initial guess values of HTVC and HTVO of 1. What will allow us to do? It will allow us to cross-plot the residuals against the converged solution and see how the solution has improved through surrogate optimization. I'll run this tuning. The validation run is typically very quick because it involves only one evaluation of the model. So in order to examine the results, we'll open them in a Ricardo post-processing tool R-Post. Let me load straight away the validation run, which is the second tuning. Okay. First, we can examine the convergence progress of the surrogate optimization process. So in tuning progress, we have the values of the cost functions, but it can be more indicative to look at the actual values of the tuned parameters. So if we look at HTVC and HTVO, we have here the best evaluated value, which we can cross-plot against the evaluations. The results clearly demonstrate that the process has converged, so the values of HTVC, HTVO stopped changing. What about the accuracy? We were trying to match airflow and torque, so let's have a look at airflow first. In my model, under parameters, I have my target airflow, and in summary data, I have the best evaluation of the model, and I have the airflow sensed in this best evaluation of the model, so we can cross-plot the two. We can see that the agreement is pretty good. What about the residual? Similarly, I can plot the residual of airflow, and it can be indicative to look at it in relative percentage values. And for reference here, we can also plot the airflow residual of the initial state. Again, as a relative percentage. We can see that the results have improved substantially by comparison with the initial guess. Initial guess had maximum error of 16% on airflow, whereas the converged results, the error is about 5.2% maximum. Let's have a look at torque. Similarly, we have a parameter for torque, which was our target, and the corresponding sensor with the best evaluation. And the residual for torque. As well as the residual for torque from the initial values of parameters. The improvement is even more obvious, so we can see that the initial guess values had values of torque deviation from the reference date of 40% maximum, whereas the converged values are within 5%. So as a result, we have improved our model substantially and tuned it to be within 5.2% of the test data, reference data for airflow and torque over 2 minutes of run on 72 cores. Finally, let us quantify the quality of the solution. In order to do that, we'll consider residuals for the best evaluation for the target airflow and target torque, and plot them as histogram against relative percentage, which allows us to add percentile annotation at 95%, for example, as our normal measure. Looking at the results, we can see that 95% of points for airflow are within 4.9% of deviation, and 95% of points for torque are within 5.3% of deviation, which indicates a great performance from the surrogate optimization process for this model. For the simple model which we have considered, it's sufficient to have two tuned parameters to match airflow and torque, and it's a good illustration of the process of calibration in R-Desk Tuner and its accuracy and speed. For more complex models, the number of parameters may need to be increased. For example, in this case, we are looking at the calibration of 4-cylinder 2-liter direct injection turbocharged gasoline engine from a leading OEM, and the engine outputs requested include airflow, torque, catalyst exit pressure, and temperatures of piston liner and head. The tuned parameters then expand, and apart from HTC at IVO and IVC, we're also including catalyst friction multiplier, HTCs, for piston liner and head, so 6 parameters in total for 6 targets. The results over 40 operating points show that for airflow, 95% of the operating points are within 5.5% from the reference data, and the similar value for torque is observed for IMAP. 95% of the points are within 5.5% of the reference data. The piston temperatures, liner, head temperatures, again, we have similar values, 95% of points within 4.2%, 7.1% and 2%, and catalyst exit pressure, 95% points within 1.6%. In our simple example, also the simulation has concluded in 2 minutes. So in a more complex example, however, we can take full advantage of linear scalability. Let's consider another example of a 2-liter 4-cylinder direct injection twin-turbo gasoline engine. In this case, the tuned parameters also include, apart from HTCs at IVO IVC, exhaust manifold HTCs multipliers for left and right turbines separately, and it's running predictive combustion, so turbulence model parameters enter into play, production, dissipation, compression multipliers, and combustion model parameters, burn area decay exponent, reference spark radius, and engine speed exponent. Altogether, we have 10 tuned parameters. The engine outputs total airflow torque, two control temperatures, turbine inlet left, turbine inlet on the right, and combustion parameters, peak cylinder pressure, crank angle for 50 degrees burn, and burn duration 10 to 90. So the engine runs at 0.31 real-time multiplier on Xeon E5 2650 processors, and we're looking at 340 operating points of the map. Considering the simulation time, as we increase the number of cores from 10 to 160, we can see that the scalability of the process is linear, and at 160 cores, the calibration completes in 60 minutes. In summary, digital twin model calibration can be a complex task. However, using scalable surrogate optimization can substantially simplify and accelerate this process. It makes it possible to tune simultaneously all parameters of the model and account for correlations between these parameters, for example, between heat transfer and combustion. R-Desk Tuner for WaveRT gives our users access to a robust, accurate, and scalable process for model calibration, and allows them to calibrate models quickly by utilizing either multi-core workstations or high-performance computing resource.